Welcome back to ECE 442-542. As way of announcement, homework number 1 is due on Monday, the 30th. If you're in the online course, you need to make sure that your proctor agreement form is submitted to the Dropbox on D2L. Homework number 2 should be posted, and you may be able to do some of that after today's lecture or even before, but you don't need to do it during class today. Homework number 2 is due a week from Monday, and our first exam is 2 weeks from today. And I was trying to get D2L or exam number 1 review material available, but it's not yet there. Hopefully it will be its own unit under unit number 2 on D2L on the content page. That's the plan. And then you can look at some previous exams, practice exams, to get ready for exam number 1, which is scheduled for the 8th of February. Today what I want to cover is this connection between the S-plane and the Z-plane, and before we do that, we'll try to interpret what Z represents as this complex number. That's now when we move into the frequency domain, what does Z represent? Maybe it's a little bit more intuitive than what S represented in the frequency domain when we were dealing with continuous time variables. Then we will talk again about stability in the discrete time setting and show why the poles need to be inside the unit circle in the Z-plane. We will again cover the rule of thumb for sampling, and we'll look at an example of what that looks like when we sample at 30 times the closed loop bandwidth. We will then start with a difference equation in the time domain and convert that by doing this operator or applying the operator Z or Z to the minus 1 to that time domain difference equation to produce a frequency domain expression, which we can then find a ratio of the output over the input to find our transfer function. And that will give us one way to then go from the time domain into the frequency domain. Now that we've been playing with this Z a lot, let's now use it to define the Z transform. We'll define the Z transform, and then we will start applying that Z transform to some common time domain waveforms, and you will start to see Z transforms in the frequency domain as they are connected or related to the time domain waveform that you're seeing in the time domain. And that will be similar to what the impulse response might have looked like in the time domain, continuous time domain, what the unit step looked like, what an exponential waveform looks like, what a sinusoid, what an exponentially damped sinusoid. We'll do those same kinds of waveforms in discrete time and see what their Z transforms look like. We need to be able to do that for exam number 1. Interpretation of Z. And we are going to do this based on where you've already been. I'm assuming that you still remember a little bit about Laplace transforms. And what does the Laplace transform look like when we're dealing with a delay? If we had now the time domain waveform, a generic waveform x of little x of t, if we Laplace transform it, there's the definition of the Laplace transform. It's capital X of s is this integral from 0 to infinity. That's a one-sided. Typically, we've been dealing with the time domain waveform defined on the non-negative values of time t in the time domain. We are integrating over time from 0 to infinity, and we're weighting this time domain waveform x of t with this complex exponential e to the minus st. That we could apply to a generic waveform or a general waveform, little x of t, and produce its Laplace transform expression. If we now consider delaying that little x of t in the time domain, what does its Laplace transform look like? And I'm suggesting that it looks like the original, capital X of S, with a slight modification. If you now, in the definition for the Laplace transform, if you now replaced little t with t minus t naught everywhere in the argument of that integral, what's going to happen to that expression? You will now have x of t minus t naught. T naught again is fixed. It's a fixed time delay. So view it as maybe 1/2 of a second. Now you want to know, oh, I have the Laplace transform of x of t. What's the Laplace transform of x of t minus 1/2 look like? Where 1/2 is a delay in that waveform. If you replace, and you can go home and do this tonight if you're not seeing it, but replace little t with t minus t naught and try to rearrange or maneuver that expression around, and what's going to happen? Do you see that in the exponent that you have e to the minus s times a quantity, t minus t naught? What did we say t naught was? It's a constant. And we're integrating with respect to t. That constant, e to the minus s minus t naught, is a constant. We can factor that out of that integral. And then we're essentially left with what we started with, capital X of S. Because if you take the differential of t minus t naught when t naught is a constant, the differential of t minus t naught is dt, and we've now come up with the integral from 0 to infinity of x of a new variable, e to the minus s new variable, d new variable, and we've factored out an e to the minus t naught s. And this now is due to the delay. Now we simply scale this Laplace transform quantity, capital X of S, by this e to the minus t naught s. So if t naught has a numerical value equal to 1 sample period, say now t naught is capital T, that's our sample period, then 1 sample period delay, which in the frequency domain of the Z transform becomes z to the minus 1, now we can relate those two expressions. Now this sample period delay would equal e to the minus t naught s, which is e to the minus ts, which if you just reverse the t and the s, you get e to the minus capital T or s, or e to the minus s t. Or what have we now just said? Now we know, or we now have an expression. We're saying z to the minus 1 is this e to the minus ts, where t is our sample period. Or if we wanted to rethink that in terms of maybe just in terms of z, what does little z equal? What's this complex variable z equal if z to the minus 1 equals e to the minus ts? Or if we look at that original expression, it's now 1 over z is equal to 1 over st. The numerator looks the same. What's the denominator? That's what I'm really saying here. Z is equal to e to the st. And what was e to the st? That was an operator that was corresponding to a sample delay e to the minus st was. This is now e to the st. This is equal to, now z is equal to a 1 sample period advance. This is now an advance in time of 1 sample period. Or you could say that this is now the definition of this complex variable z in terms of the complex variable s. So if you had an expression that was a function of s, could you now use this? Or if you had a function, a transfer function as a function of z, you could replace z everywhere with e to the st, and that would give you this expression in s. But we are going to just lump this in, but this now gives us a interpretation of what z represents. Z is now like an operator that's corresponding to a 1 period advance in the time domain. But we need to remember that this complex, or z, as a variable is a complex number that we will use as a frequency variable or a frequency domain operator for discrete time systems. If you see z to the minus 1, you can think, oh, that's like a delay in the time domain of 1 sample period. But this is now in the frequency domain. This is now an operator. Let's look at what this corresponds to if we look at points that we're familiar with in the S-plane and map those into the Z-plane. You're familiar with the complex S-plane. It has a horizontal real axis and an imaginary vertical axis. We're going to introduce another complex plane, very similar. The horizontal axis is the real axis, the vertical axis is the imaginary, but that will now be the Z-plane. So we want to know how is the S-plane and related to the Z-plane. We have two different complex planes. Here's one, which is the S-plane. Here's the imaginary of S, and here's the real of S. Let's say this is now the S-plane. And we want to connect that or relate that to another complex plane, which has the real part Z and the imaginary part of Z. Z is a complex number. It has a real part and an imaginary part. And to give us something to think about, suppose that we now look at or examine a particular complex value of -3 plus J2 in the S-plane. And we have just now derived or developed this relationship between Z and S. That relationship now said that Z is equal to e to the st. So that now this S-plane is related to the Z-plane, and where is this going to go? Well, we will show where that goes, but let me just indicate that that's over here where this might be 1. It's now plopped over to that location, roughly. And we're going to find precisely where that is for this value of S equal to -3 plus J2. But let's look at S a little more closely as far as what it looks like. S is now, typically we say, oh, that's maybe minus sigma, the real part, plus j omega sub d, where the real part gives us the damping, and omega sub d gives us the damped frequency of oscillation. And we, if we want to look at an example, we'll say, oh, minus sigma is minus 3, and omega sub d is 2. We may show where this comes from in a minute, but for now, let's just assume that we are given a sampling period of 0.04 seconds, or 40 milliseconds. 0.04 seconds will be 40 milliseconds. What we want to do now is start to understand what we end up with when we look at z equal to e to the st. That's how z and s are related. And we sort of know what we have when we have a pole at s equal minus 3 plus j2. What does that correspond to if you had its twin, its conjugate, down below at minus 3 minus j2? If I said inverse, or what's a time domain waveform that has roots or poles at minus 3 plus and minus j2, what do you see in your mind? Maybe not a hypotenuse from an earlier class, but you now have poles at minus 3 plus and minus j2. That's in the denominator of a Laplace transformed quantity. What do you see if you now take that into the time domain or inverse Laplace transform? Do you remember? A damped sine or cosine. You now have an exponentially damped sine or cosine. The damping is influenced by the minus 3, so you have an e to the minus 3t. And the shaking, the frequency that it's shaking with, is that omega sub d. It's 2. You now have something that looks like e to the minus 3t cosine of 2t. Or you could have another component that's e to the minus 3t sine of 2t. And you have some combination of those two. That's what you have in the continuous time. Let's now look at what that looks like in the z-plane. We now know what S is. We have a particular way of parameterizing S. We said S is minus sigma plus j omega sub d times t. And we simply have to remember our algebra relative to exponents, how to play with exponents. This now is equal to, let's distribute that capital T, or the sample period, among the real and imaginary parts of that complex number S. And we have now this exponent. Let's break it into, well, I'm getting ahead of myself. Let's distribute the T plus j omega sub d t. With two parts to the exponent, we can now create two different multiplied together quantities. We can now write that equivalently as e to the minus sigma t times e to the j omega sub dt. And what we will start to do is we will now say, oh, we now have identified this complex number z as having a magnitude piece. Here is our magnitude piece. We might call that capital R. And this is a complex exponential. We might just collapse that omega sub dt into an angle theta sub d. So that now we started in the S-plane at minus 3 plus j2. We've now found that it is equivalent to some location in the z-plane at some radius away from the origin at an angle at an angle of theta sub d. Here, R is equal to e to the minus sigma t, and I'm doing it now for the generic sigma and omega sub d. We'll just in a minute replace that with the specific numerical value that we said was our example of minus 3 plus j2. But right now, if somebody wanted to know what r was in terms of s, or a piece of s, it's now e to the minus sigma t, where minus sigma was the real part of that s. And omega sub d was the damped frequency of oscillation, and that gives rise to some angle. Let's now plug in some numbers if these variables are just floating around in your head. Let's look at the specific numbers that we talked about before. Suppose S, again, is this minus 3 plus J2, and capital T is 40 milliseconds, or 0.04. Now we can say Z is equal to e to the S, which is minus 3 plus J2 times T, which is 0.04. Or this now becomes e to the minus 3 times 0.04, e to the j, let me just go ahead and multiply 2 times 0.04, or that's now 0.08. Or what is that? Well, that's now e to the minus 0.12, and that's just a number. E to the j 0.08, and remember that this particular value in this exponent is in units, or has units of radians. It's not degrees. This is now in radians. And this again was our r. If you pull out your calculator, hopefully it has an E button on it. And you can now say e to the power, or raise it to, minus 0.12. What's that going to produce? It's actually going to produce a number that's less than 1 because it's a negative exponent, and that number to 3 significant digits is 0.887. And if you converted 0.08 radians into degrees, what would that be? What is a tenth of a radian? Or what's a radian? 2 pi radians make what? A circle. How many degrees are in a circle? 360. So we know 2 pi radians are the equivalent to 360. And 2 pi, in rough terms, is 6, right? Because I can divide 360 by 6. So 1 radian is about 60 degrees. It's actually a little less than that. It's 57. But now 1/10 of that, I'm just pulling these out of the air? No, you can divide. So I know 2 pi is 6.28, and I can divide that into 360 to obtain 57.2958. That I just pulled out of the air, didn't I? I did that before class. But now this is, in terms of degrees, this is e to the j, a little bit less than 6 degrees, right? If it's a tenth of 60, and 60 was an overestimate of 1 radian. So this is now j of 4.58 degrees. Can you now not draw a complex number that has a length of 0.887 at an angle of 0.458 degrees? Now you need your protractor and your ruler and your straight edge. Oh, now we're having fun, aren't we? So what do we have? We now have our z-plane. If this is of length 1, now we go out to basically 90% of that distance. And this may not be accurate, so you could get your protractor, maybe it'll have to be really finely resolved to measure 4.58 degrees, but you get the idea. We are now out here. Oh boy. That was supposed to be a straight line. It looks straighter for me. All right, doesn't look straight for anyone. But let's try that again. Oh, that's almost perfect. But now it's 0.8, whatever I said, 0.887 in length. And what's this angle? That's supposed to be 4.58 degrees, which means that with a sampling period of 40 milliseconds, or 0.04, a complex number in the S-plane at -3 plus J2 mapped into a point in the Z-plane of magnitude 0.887 at an angle of 4.58 degrees. And that's what you're going to have to start connecting. Let's make some observations of what we have seen or observed from this relationship between S-plane and Z-plane. First observation, when we looked at the magnitude of r, in this case it was e to the minus 3t. As long as t is a positive number, what do we know about the magnitude of e to the minus 3t? It's less than 1, is it not? If you remember, let's say this is the real part of s, let's call that x, and now if I sketched e to the x, what would that curve look like? Give me a point that I can sort of pin on that grid. What would be e to the 0? That's 1. That's easy to find, isn't it? So now if I find 1, there is e to the 0. What is e to the 1? What is e? Do you remember? If you don't, you can look it on your calculator, can't you? You can evaluate it. It's 2.7, roughly. So now at 1, if we were over here at 1, we are at 2.718. So let's say that's up here. What is e to the minus 1? What's 1 over? So we've now said that e is 2.718. What's e to the minus 1? What's 1 over e? What's 1 over 3, roughly? 1/3, isn't it? So if we come back to minus 1, where are we at? Well, we're actually at 0.37. Remember that exponential decay, you're at 37% of where you started if after e to the minus. So this is now 0.37. What's e to the minus 2? Well, it's that quantity squared. And we're just decaying more and more. Or this e to the x, if I could sketch, does that as a function of a real number exponent. Well, that's an ugly 3, isn't it? All right. You convinced me to relabel that, but that's now not much better. But that point, e to the minus 1, is 0.37. What do we have? Well, if we had a negative exponent, or if we are in the left half complex S-plane, where is that blue curve relative to a value of 1? It's always below 1, isn't it? R has a magnitude less than 1 if we have a negative exponent. What happens if we have a positive exponent? That's over here. Now we're bigger than 1. That's about one of the key things that we need to keep track of in this complex Z-plane. is what is that S value? Is S negative? Is it positive? And now that tells us something about the behavior of our discrete time system. That's one observation. A second observation is that values of S, which is from this diagram actually, in the left half plane well, let me say left half S plane. I have too many planes here to keep track of. In the left half S plane, map to values of the complex variable z, where? If we are in the left half S plane, now we are over here, aren't we? What's that blue curve for e to the x? Where is that numerically? Or if I could give you a hint, where is it relative to that highlight? It's always less than 1, isn't it? So now if I'm putting dots in the complex z plane for any value of s in the complex or in the left half complex S plane, they're all going to be in a unit circle in the Z plane. Their magnitude is less than 1. Values of S in the left half plane, left half S plane, map to values of Z inside the unit circle. Unit being a magnitude or value of 1. Another observation, theta sub d that we had defined to be omega sub dt is just some angle. And that angle will depend on what the damped frequency is equal to, omega sub d, and what our sampling period is, capital T. In the complex plane, Z plane, here's real Z, and here's imaginary Z. If somebody gives us theta sub d, or if they give us omega sub d and capital T, we can sketch now an angle, theta sub d, which is equal to omega sub dt. And what's this distance here? That's the r. Another rule of thumb that we didn't necessarily observe with this example, but I've already told you, is how to select capital T, the sampling period. We select capital T which is called the sample period, to be 30 times the closed loop bandwidth. Let's look at an example. Suppose we want a closed loop bandwidth of 5 radians per second. What I'm saying there is this is now what we have been calling omega sub c. Omega sub c, our closed loop bandwidth, is 5 radians per second. And if we're not used to thinking of radians, which are these 57 degrees, we're doing 5 of those every second. We're used to thinking maybe in hertz. How fast is this in terms of our closed loop bandwidth in cycles per second? Or if we went 1 cycle per second, we would have had to have gone 2 pi radians, which is 6.2. Is this 6.2? No, it's not quite that. So we're not going quite 1 cycle per second. We're not even at 1 hertz in terms of a closed loop bandwidth. We're a little bit less than that. If you wanted to see that, you would say, oh, omega sub c is, what did I tell you? Remember that until you retire? Omega is 2 pi f. So now omega sub c is 2 pi f sub c. F sub c is now omega sub c over 2 pi, and this is now 5 over 2 pi, which is 0.7978, or it's about 0.8 cycles per second, or 0.8 hertz. That's what 5 radians per second looks like, or is, as a closed loop bandwidth. What do we need to do in terms of sampling? Well, our rule of thumb tells us that we want to sample omega sub s needs to be 2 pi f sub s, which we could say is 2 pi over t, needs to be 30 times omega sub c. Where in all of this, let's define some of these omegas and f's. This is now our sampling frequency. With units of radians per second. F sub s, if I can confuse you, is also a sampling frequency, but it has units of hertz, or cycles per second. So you have to be told what are the units of that sampling frequency. If somebody just says, here's your sampling frequency. F sub s is a sampling frequency. With units hertz or cycles per second, and capital T is our sample period. And that has units of seconds, where F sub s is simply the reciprocal of T. But in this, what do we know? We were given omega sub c. We know 2 pi. We want to find what is F sub s, or what is capital T. So we can solve for that unknown in this expression. Therefore, capital T is equal to 2 pi over 30 omega sub c. Just solving for capital T in that right-hand equality. But we've already said that omega sub c was 5. And now we can do some approximations. So let me just, because T is not hard and fast, it's just a rule of thumb. Let's say this is now approximately, let's say that pi is now, let's say that that's roughly 3. As pi is 3.14. If we make it 3, we've made T smaller, and that's finer resolution. That's a good direction to approximate. So instead of T being determined by 3.14, we've just reduced it down to 3. So we've made T smaller. But 3 and 30 are nice, so that now we have 2 over 10 times 5, or 2 over 50, or 4 over 100 is easier, or 0.04. By sampling at 30 times the closed loop bandwidth, if we had a closed loop bandwidth of 5 radians per second, we would want to sample our sample period to be 40 milliseconds, using that rule of thumb. And again, we had some approximations in there. We reduced pi to 3, but that's okay. It's just a rule of thumb. T then is this 0.04 seconds, or if you want to make it sound better, it's 40 milliseconds. Instead of saying 0.04, you can say, oh, it's 40 milliseconds. What's that in terms of the sampling frequency in cycles per second? Well, that's just 1 over t. This is 1 over 0.04. We've already written that as 4 over 100. Or we're sampling at 25 hertz. And does that make sense? Omega sub c, our closed loop bandwidth, was a little less than 1, and we wanted to sample 30 times that. Well, if omega sub c was 1, we should be sampling at 30 hertz. And here we're sampling at 25 because our omega sub c was a little less than 1 hertz. Questions on S and Z and sampling? Yes. So now the question was, what do we call it when we go from S to Z? We call it S to Z. We'll call it later in the class a discrete equivalent. So we might have a filter, we might have a system that's in the S domain, and we may want it to come into the Z domain. We will call that a discrete equivalent. So we're now finding the discrete equivalent to some S domain expression or relationship. But typically we'll just say S to Z for now, until we get to that section of the class. But it's a discrete equivalent. We're simply moving from the continuous time into the frequency, from the continuous time into the discrete time in the frequency domain. So let's keep in the discrete time setting and look at how to go from the time domain into the frequency domain using this Z variable. Let's now look at an example where we are converting a time domain linear difference equation into the Z domain to actually find a transfer function. And this is similar to what you did before when you took a differential equation and went and found a transfer function. You might have a differential equation that describes the governing relationship of some system, a circuit, and you wanted to find the transfer function associated with that. Now we have a time domain linear difference equation, and we want to now find the transfer function in the frequency domain that describes that relationship. Here we're going from the time domain into the frequency domain. Let's start then with the difference equation. Which I will keep as a variable, or keep it very generic. Suppose that I now have y of n plus a sub 1 y of n minus 1, or 1 delay, plus a sub 2 y of n minus 2, plus a sub 3 y of n minus 3 plus a sub 4 plus, no, let's quit with a sub 3 equaling b sub 0 u of n, and u is just a generic input waveform, y is my output waveform, plus b1 u of n minus 1. That's the linear difference equation that might describe a filter, it might describe some dynamical system. What we want to do now is use our knowledge of the Z-transform to convert this into the frequency domain. Or using, now instead of a script L, this is supposed to be a script Z. Hopefully that's okay. That's now a script Z that's operating on y of n, and the notation that I will use is I will now say that's now capital Y of Z with square brackets, because now I'm in the frequency domain. This is a Z-transform operation. And you might say, what? What is Y? Well, we've actually implicitly buried the sample period. Somebody might write this as Y of nt. Sometimes we have the t shown, sometimes we don't. But it's Y of n. To be cleaner or maybe easier to write, I may just write Y of n, which is what I did in my linear difference equation. But you would have to be told if it was indeed something that was sampled, if it wasn't a fundamentally discrete time relationship, now you would have to know what is capital T. But a lot of times it's not shown in the equation. If this is now the Z-transform of little y of n is equal to capital Y of Z, what do we know, or what could you say if I now said let's Z-transform y of n minus 1? Or this is now, if we wanted to think of it, this is now n minus 1 times capital T. This capital T may be implied in our expressions for y. What do I want on the right-hand side of that expression, or of that equality? How many delays do I have in the argument of my time domain waveform? 1. How do I represent a 1 sample period delay in the frequency domain? Z, that was buzzing, wasn't it? Z to the minus 1, right? That's a 1 period sample delay. This now can be, oh, I almost broke my stylus. I better quit killing bees. Z to the minus 1, capital Y of Z. That's really all we need in terms of understanding to take this linear time domain difference equation into the frequency domain. If we know this, these two relationships, what would be Y of n minus 2? Z transform. Z to the minus 2 times capital Y of Z. Now we're good to go. What do we know? If we Laplace transform, whoops, what happened? Little y of n, what's that? That's just capital Y of Z. What's the next piece? What's the Z transform of little a1 y of n minus 1? A1's a constant. That slides out, and we know what y of n minus 1 does. We now know that this is a1 z to the minus 1 y of z plus a sub 2 z to the what? Minus 2 y of z plus a sub 3 z to the minus 3 capital Y of z, and that's equal to b sub 0. What's the z transform of lowercase u of n? If the z transform of lowercase y of n was capital Y of z, now we just have to hit the shift key and capitalize u and give it what? Argument of z. We now say that we have all of this on the left equal to b sub 0 capital U of z plus b1 z to the minus 1 u of z. Can it be any easier to convert a difference equation, time domain difference equation, into its frequency domain expression doing the z transform? It's just an operation. Now we can combine or factor out the common capital Y of z and the common U of z in this to now have 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3 times y of z equaling b sub 0 plus b1 z to the minus 1 u of z. If we want a transfer function, y is our output, u is our input, we can now write capital Y of z over u of z is equal to b sub 0 plus b1 z to the minus 1 all over 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3. Well, that looks odd. Unless you saw my notes or looked at the notes from Monday. Oh, don't upset me. You all studied those thoroughly. What did I say at the very end? After I finished here, I said I'm going to add some more notes at the end of class and provide those to you on D2L. Is it? Well, it varies. Sometimes we keep this in terms of z's with negative exponents, but sometimes we want to write it in terms of z's with positive exponents. How could I write this same transfer function in terms of positive exponents with z? Many different ways of doing it. You could factor out a z to the minus 3 from the numerator and the denominator, or you could multiply by 1, where 1 is this special one of z cubed over z cubed. Sometimes that's easier to think of. If I multiplied that by 1, I haven't changed anything, and my 1 is z cubed over z cubed. If I do that, what do I end up with? I could also say that y of z over u of z, if I multiply b sub 0 times z cubed, what do I have? b0 z cubed. Can that be any easier? What is b1 z to the minus 1 times z cubed? Now we simply do the same thing in the denominator. We had 1, well, we're scaling that by z cubed. We're hitting a1 z to the minus 1 with z cubed, etc. Now we have a transfer function in the frequency domain that describes that same dynamic relationship of input to output, except now we're in the z domain. And you could find, if I gave you a's and b's, you could find the roots of the numerator, which would be zeros of the transfer function, or you could find roots of the denominator, which would be poles of your transfer function. And you could put those as x's and o's, poles and zeros in your z-plane. How many poles do you have in this particular system? What's the order of your denominator polynomial? 3. I apologize for those that are listening. You didn't see me scratching with 3 fingers. Luckily, it's third order, right? Okay. Let's move on. How many zeros do you have? 3. Now it's a little different than in the continuous time. But now you have, where are your zeros? You have a z squared times something z plus something. So 2 of your zeros are at the origin in this particular case. Well, we keep playing and talking about z's. Let's define the z transform as far as an expression. So that if somebody gives you a waveform, you can find its z transform. If somebody gave you a unit step, you could hand them the Laplace transform of that unit step. Yes? Just fall asleep and shake your head up and down, right? Humor me. You need to know some of the Laplace transforms that you've seen before. Let's now define the z transform, and we will start by remembering, or trying to remember, what we know about the Laplace transform. I've already written this down earlier. The Laplace transform of a generic time domain waveform little x of t, we were calling capital X of s, and that was this integral from 0 to infinity of x of t weighted by some kernel, which was a complex exponential, e to the minus st dt. So that now this is actually weighting all of x of t. We need to know what x of t does for all time from 0 to infinity. We weight it with this complex exponential. We integrate that product, and out pops a Laplace transformed expression. Now we want to talk about z transforms. Now we don't have an x of t, we have a waveform only available at discrete instances of time. It's not continuous. Now we have a little x of n, or a sampled version of x of t in our z transform. In this expression, then, we have an x of n. But if we are doing something with discrete values, do we integrate? No, we don't integrate with discrete instances. Now we sum. The integral now becomes a summation. And this kernel now, what did we know about the relationship between s and z? Z was equal to e to the s capital T, wasn't it? So now, if we plugged in little t, a sampled version of little n capital T, now this becomes z to the minus n, where we are using t is equal to nt, so that now we have e to the minus s nt, so that we have e to the st to the minus n, and there's our z to the minus n. And we may talk about different sidedness of this z transform. Let's just now say this is our capital X of z. but we might have this defined only for non-negative values of n, or for n equal to 0 to infinity. This is now one-sided. Or we might have a Z-transform that's two-sided, which is now a sum from minus infinity to infinity, x of n, z to the minus n. Maybe that looks a little abstract. Let's apply this to some common waveforms that we can visualize or think about. Let's look at the Z-transform, applying this expression, this infinite sum, to some common little x of n's. About as common as we can get is a, what I will call the unit pulse. And notice that's not the unit impulse. Somebody might call it that. I want to just prefer to use pulse. This is now defined as little x sub a of n to be 1 at n equal to 0, and it's 0 everywhere else for all of other arguments of its domain. If we needed to sketch this in the time domain, it looks very basic. It now just has a value of 1 at time 0. Whoops. I guess I should label my... Everywhere else, it's equal to 0. That's what this looks like. So now, if you hit your system with a pulse, a unit pulse, you hit it with 1 at time 0 and nothing thereafter. It's similar to an impulse where you hit your system with an impulse in the continuous time, which has a magnitude of infinity and it has an infinitesimally small width. Now this is a little easier to think about. You just hit your system with a 1 and watch it ring or respond. What's the Z-transform of this time domain waveform? Let's plug it into the expression for the Z-transform. We are now saying, what is capital X sub A of Z? That's now this sum, and now it isn't even defined for negative n, so let's just start with n equals 0 and go up to infinity. It's now x sub a of n, z to the minus n. If you wanted 1 point on the final exam, you might get it if you just write this. X sub a. Find the Z-transform of little x sub a of n. Oh, well, at least you can write this down, and then the juices will start flowing, and you'll just get it. What is it? Well, in this case, it's pretty easy to just start plugging in values. This is now x sub a of 0, z to the minus 0, plus x sub a of 1, z to the minus 1, plus x sub a of 2, z to the minus 2, etc. But what are these? What? More z's, but these aren't. These are sleeping z's, not bz's. We're doing the Z-transform, so I guess all z's are allowed, right? You're trying to correct me, and I hear you. I had an A somewhere, but today I would have gotten maybe an E, right? A failing grade, so I'm going to withdraw. Today's the last day to withdraw. I can still do it. Where was I? Oh, here is x sub a of 1, x sub a of 2. Is that better? What are those values? This one is 0. This one is 0, as are all the others. What's this one? 1. What do we have on the right-hand side? What's z to the 0? 1. Capital X sub a of z, the z transform of a unit pulse, is 1. That was pretty easy, wasn't it? Let's remind ourselves of what we can do a little bit more of by starting with the unit step in the continuous time case. So here is an aside. This is a memory lesson. Suppose u of t, now I'm changing up the floor plan a little bit. Now u of t is the unit step. It's not a generic input. Let's say this is the unit step, and we're now in a continuous time argument. T is a continuous time variable. What's capital U of S? What's the Laplace transform of the unit step? What's the Laplace transform of a constant? If you plugged 1 in for x of t here and integrated from 0 to infinity, what are you going to have? 1 over s. Thank you. This is now 1 over s, right? So the Laplace transform of a unit step is 1 over s. What's that look like pictorially? Time domain. There's time. Here's u of t. There's our unit step. In the frequency domain, what's our pole zero diagram look like in the S-plane? Do we have any finite zeros? Do we have any finite values of S that cause capital U of S to vanish? Any finite zeros? No. There's nothing in the numerator as a function of S, is there? Where's our pole? Do we have a pole? And where is it? It's the value or values of S that cause the denominator to vanish. What value of S causes the denominator to vanish? Or for the whole thing to go to infinity, to be a pole? It's at 0. So we now have a pole at the origin. Whoops, I wanted that to be a different color. There's our pole. Let's look at what we have if we do a unit step for a discrete time system. What does that look like? Well, now this is lowercase x sub b of n. It's only defined at these discrete instances, and it has a value of 1. The ellipses means this goes on and on and on forever. It's a unit step, but it's 1 only at 0, at 1, at 2, at 3, etc. Or this is now x sub b of n in equation form is 1 for all n greater than or equal to 0. What's the z transform of little x sub b of n? Let's see if we can compute it. We now are going to have capital X sub b of z is equal to this sum from n equal minus infinity. Again, you're searching for points here. N equal minus infinity to infinity of x, little x sub b of n, z to the minus n. For what values of n is this even x sub b of n non-zero? For negative values of n, it's 0, isn't it? So we can now say, oh, this is from n equals 0 to infinity. And what is x sub b of n as a function of n? What's its value? It's 1 times z to the minus n. Well, that's now x sub b of z is equal to 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 plus etc. That's the z transform of the unit step. But it might be nice to have a closed form solution. We know what the Laplace transform of a unit step was. What? It was a ratio of polynomials in S. It was 1 over S. Be nice if this looked something like that. Does this? No. So let's look for a closed form expression of this. And this might start to look similar to what we've already done in an earlier lecture. What's the closed form expression going to look like for capital X sub b of z? Well, we know x sub b of z is equal to 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3, etc. But this is actually what? This is just a geometric progression, isn't it? Where each factor has the same ratio difference of z to the minus. This is now z to the minus 1 to the 1. This is z to the minus 1 squared. This is z to the minus 1 cubed, etc. Each one is being multiplied by z to the minus 1. The common ratio is z to the minus 1 in this progression. Well, that maybe gives us a clue as to what we can do. We can now say, oh, here is x sub b of z. What if I hit that with z to the minus 1? Every term on the left, I just multiply that by z to the minus 1. Now every term on the right, what happens? The 1 becomes z to the minus 1. The z to the minus 1 becomes z to the minus 2. And remember, this has an infinite tail. Plus z to the minus 3. So it looks the same in the tail. The tail looks the same, right, for this expression. It's just in that very first term that it's different, because we multiplied everything by z to the minus 1. But now I can take the difference between these two rows of expressions. Let me subtract the bottom row from the top row. Or I now have 1 minus z to the minus 1 times capital X sub b of z. And what do I end up with on the right? If I subtract the bottom from the top. Every term is the same except for the very first one in the top, and I'm left with 1. Now, when is that top blue expression well behaved? When does that make sense? When will that sort of sum to a good value or a bounded value? We want that z to the minus 1 factor to be less than 1, don't we? So that when we keep raising it to higher and higher powers, it shrinks. So for this to be well behaved, we actually need this z to the minus 1 less than 1 for that to actually converge. And if that's the case, then we can now solve for x sub b of z. That's now 1 over 1 minus z to the minus 1. It converges when z to the minus 1 is less than 1, but we can clean that up a little bit. That's 1 over z less than 1, or that's the magnitude of z bigger than 1. And we can also get rid of that negative exponent by scaling or hitting that whole thing by 1, where 1 is z over z. Where we now can say that the z transform of our unit step is z over z minus 1 when the magnitude of z is bigger than 1. And in the z-plane, this is now the z transform. Does that look sort of like what we had for S? I'm sorry, in the S domain, it was 1 over S. We're going to find that S equal to 0 is similar to Z equal 1. So now, where is our pole at Z equal 1? We actually have a 0, a finite 0 here. And if we drew the pole 0 diagram, or this, the complex plane, we would say, ooh, boy, that's supposed to be the unit circle, not an apple or, well, this is 1. Let me just label it, minus 1. This converges. This is now our region of convergence for values of z outside of 1. And we'll get more into that the next time we meet. But what I've shaded is the region of convergence, which is where that particular waveform was nice or well behaved. It was for values of z outside of 1 or bigger than 1. So the region of convergence is outside of 1. Here's j and minus j, and our pole was at 1, and we had a 0 there. We'll now, next time, look at exponentials and maybe exponentially damped cosines to see what those z transforms look like. But we've started to see z transforms of some common waveforms, and we'll pick up there next time.